This is the third lecture in our fluid mechanics primer, and the goal of today's lecture is to look at stress and the momentum equation, and it's far and away the hardest and most involved of the lectures I'm going to give you. It's going to start from a fairly simple premise, which I think you'll be pretty happy with, and that is just the notion that force can be considered to be proportional to the acceleration, with mass in there as well. So that's Newton's second law, and it should be fairly familiar to all of you. Let me just tidy this one up. And of course, once again, we're thinking about how to apply this in a fluid. And in a fluid, we're going to think of mass times acceleration as being the rate of change of the momentum. And the momentum is rho times u, okay? And then the forces are going to be any force that can act on a fluid. And I've shown this for our control volume schematically here on the right. This is our control volume V. And the forces I'm going to consider here are body forces such as gravity. And here I define the vector of gravity to be 0 in the x direction, 0 in the y direction, and negative g in the z direction, where g is 9.81. And the other thing we've got here is stress, and what I've drawn here is the stress tensor, sigma, and the stress vector is sigma dot n, and I'm going to talk about stress a little bit later in the lecture. But for now, you're just going to roll with the fact that this sigma here can be considered a tensor, or if you like, a 3x3 matrix, and we'll deal with the details later. So basically we're going to have gravity on the left, which is going to be one of our forces, and we're going to have stress. And they're the only things that are going to be acting on our control volume. So to write this a little bit more formally, we're going to swap sides. We're going to do d dt of the integral over the control volume of the momentum. That's rho u. And on the right hand side we're going to have our body force, which is obviously integrated over the whole volume, and that's just rho times g dv. And then we've got over all the surface of the fluid we have the possibility for stress to act, and we're going to write that as sigma, which is, remember, that tensor dotted with the unit normal integrated over the whole surface. The next steps are going to become pretty familiar to you if you've watched the last two lectures, and we're going to use Leibniz in 3D to deal with this left-hand integral. So that just becomes the integral of d dt of rho u, and we're going to have a v here, plus integral over the surface of rho u times by u dot n, okay? Now you'll notice the vector term's getting a little bit hairy here, because what we have here is actually not one equation but three equations. It's a vector integral equation, so we've got one equation for each direction, and I'm just rewriting out this last bit here, and that sort of complicates matters, and you'll just have to bear with me on that. What I'm going to do next is, once again, familiar to you, I'm going to apply Gauss's theorem to these two terms. And in this case, particularly on the left-hand side, it gets a little bit complicated. So what I'm going to do here is I'll just write a volume integral over the whole left-hand side. So we have d dt of rho u is unchanged. And now we need the divergence of all these three terms here. So the way I'm going to do that is, first I'm going to expand it out straight away with the product rule and give you rho u times the divergence of u, okay, and then we'll get the second term, which is u times the divergence of rho u, and this is all integrated over the volume. And the right hand side, well, that's also a little bit tricky. We have a rho g, that's easy, but what I'm going to do with this tensor is write that as a divergence. And this is actually all a little bit easier in tensor notation if you're prepared to stoop to that, which we won't do, at least for this part. Okay, so from here, once again we have an equation that we put over, integrate over a volume, which is of arbitrary size. We can make it arbitrarily small, so this equation applies at every point according to the continuum hypothesis, and that gives us ddt of rho u plus, I'm actually going to swap these terms around, sorry, I should have done them in the opposite order to start with, and then we have the next one is just this term here, rho u times the divergence of u, and on the right we have rho g, and then we have the divergence of our stress tensor, which we don't quite understand yet. So the next task here is to play around with this term on the left hand side, and the reason for that will become obvious once we do it. And in the derivation of the advection diffusion equation, what we did is we wrote a term like this, which was a total time derivative, and then we wrote a term which was roughly similar to this one here, u times the divergence of u. Okay, so this left-hand term just took up the first two terms of the last equation on the previous slide, whereas this one was the next one. And of course in the advection diffusion equation we just cancelled this, saying that we're an incompressible fluid, but in fact we don't need to do that in this case, and I'll show you why in a moment. We've got the same right hand side here. So what we actually do here is we're going to unwind this term as well by the product rule. We're going to get a rho times du dt, which is a much more convenient form of momentum, and by the product rule this gives us another term which is u times d rho dt. Okay, total time derivative of course. Now we can combine that with this term. We'll take this u out the front and we're left with a rho times the divergence of u with the same right hand side. Now the term in brackets here will become familiar to you if you've looked at lecture 1, because this term here is just conservation of mass, and this is always zero in any fluid, unless, for example, you have radioactive processes that are creating mass. So we can safely assume that's not going to happen here, and this whole term can disappear, and we end up with a momentum equation in its most general form, which is rho times the du dt, total time derivative, plus the body forces, plus the stress divergence. And that's where we're going to kick off our analysis of stress, because we can all understand these equations, these terms on the left, but this stress term here on the right is probably not familiar to you. So let's think about stress. What do we know about stress? Well, stress is a bit like pressure. It's a force per unit area. It's in units, newtons per meter squared. And it's we normally write a stress as being something like a coefficient times a velocity gradient. Okay. For example, let's say we have set up a little coordinate system here on the right, where we have x in that direction and y in that direction, and let's say we have a velocity field with some shear. Okay, then stress is the process by which viscosity will transfer this momentum from the high momentum regions to the low momentum regions. And you'll see that as I've written it here, we're assuming that stress is proportional to a gradient, which is very similar to the law for diffusion. And you can often think of viscous stress as being the down gradient diffusion of momentum. At least that's the way I like to think about it. So, of course, we note that stress has a direction, meaning it's a vector, but it's also applied to an area. So if we consider the edge of our control volume, the stress could have a certain direction, but the area over which it's applied also has a certain direction, or unit normal. In other words, there's two parts of information you need to understand stress. Okay? And what we often write, that's why we write this tensor, the stress tensor, to be sigma ij, okay, so these subscripts are referring to different directions, and I is the direction of this normal vector to the surface we're considering, and j, sorry, that's, shouldn't write nj, j is the direction of the stress itself, okay. Okay, so what this means is that you have a tensor which looks something like this, okay, etc. So we have 9 components of this stress tensor. We have to figure out what it does. The first thing I'm going to do with this stress tensor is I'm going to write it, I'm going to pick it apart into 2 pieces. Let's just rub that out for a moment. What I'm going to write is I'll write sigma ij is equal to negative pressure times I plus some other tensor, tau ij. Now tau is the viscous stress tensor, and pressure is something that you know and love. And the point about pressure is pressure always acts normal to the surface that you're thinking about. So it is a stress, but it's a stress that's normal to the vector you're thinking, to the area you're thinking about. In other words, it's times the identity matrix. We take P times the identity matrix as being our pressure component. Hopefully that makes sense. And we've also got this tau ij here. Now tau ij is the component of stress due to viscosity. And to get the final form of our momentum equation, we're going to make some assumptions. And these assumptions are that this viscous stress tensor is symmetric, that viscosity is constant, and that the stress is proportional to the velocity gradients. And it turns out that the most general way we can write this is to write tau ij as being dui dxj plus duj dxi, and you'll be disappointed to see that I've lapsed into tensor notation. If you don't like tensor notation, then you can see all these matrices unpacked in the handout that we gave out that's associated with this course. But what I want to do from here is I want to write sigma ij as being, and I'll go fully to tensor notation and call this negative p times delta ij plus mu times dui dxj plus duj dxi. And now we're going to take the divergence of this, and the divergence of sigma is just equal to d dxi of sigma ij, where, as always, the repetition implies summation. So what we can do here is we can write negative dp dxj plus mu times d squared u I dxj squared plus d squared uj dxi dxj, and here we're going to assume our flow is incompressible, and if we do that, then you can see out of here you can pull a duj dxj, which is just equal to the divergence of u, and so that equals 0. So this part cancels, and if you want it, again, if you want to see that unpacked, we do the matrices specifically. A matrix version of this in the handout. It's just a pain to write, really. So what that means is that we can end up writing our divergence of sigma as being a pressure gradient. Okay, so negative grad p plus mu times grad squared of u. That's what this one on the right here is. Okay, so we apply this to our formula that we had before, where we had a rho du dt, and that equals a rho g on the right hand side minus grad p divided by rho, sorry, I didn't want that rho there, copying off the primer. This is a minus grad p here, and then we have a plus mu times grad squared u, and this is our vector equation for the conservation of momentum in point form. Just to point out a few things, if we set the viscosity to 0, as we did in one of the examples on the sheet, then we lose this final term and we get an inviscid equation, which is Euler's equation, but we still have an effective pressure. It's quite common to divide through by rho, often making the Boussinesq approximation that rho is not important in the inertial terms, and that's the form of the equation that I also gave you in the sheet. And you're welcome to read up more on the Boussinesq approximation if you want to. So that's going to do for this. The next lecture we'll be looking at adding rotation to this formula, and that will be the last lecture in the series.